What is the specific problem that the proposed method aims to solve in the paper?
The specific problem that the proposed method aims to solve in the paper is estimating the hallucination rate for in-context learning, ICL, with conditional generative models, CGMs. The paper introduces a new method to estimate the probability that a CGM will generate a hallucination as a solution to an ICL problem. The method focuses on understanding and predicting errors or hallucinations that may occur when using pre-trained models like large language models, LLMs, for tasks they were not explicitly optimized for. The goal is to provide a way to quantify and estimate the likelihood of hallucinations in the responses generated by CGMs in the context of ICL tasks, without requiring external information from auxiliary classifiers and being applicable beyond language tasks.
How does the proposed method work step by step? Please provide a detailed breakdown of the methodology.
The proposed method works step by step as follows. 1. Introduction and background. The paper focuses on estimating the hallucination rate for in-context learning, ICL, using conditional generative models, CGMs. ICL involves feeding a dataset to a CGM and asking it to make predictions based on that dataset. The goal is to improve prediction accuracy for various tasks using pre-trained models. 2. Bayesian perspective. The method takes a Bayesian perspective, assuming that the CGM samples from a posterior predictive distribution over a latent parameter and data. This leads to the definition of the posterior hallucination rate, PHR, which estimates the probability of generating a hallucination as a solution. 3. Defining hallucinations and hallucination rate. Hallucinations are defined as values that are unlikely to be generated from the true mechanism. The true hallucination rate, THR, is the probability of sampling a hallucination given the true mechanism and query. 4. Posterior hallucination rate, PHR. The PHR is defined as the probability that a response will fall outside the high probability interval of the true mechanism and query. It is calculated using Dub's theorem to transform statements about the predictive distribution into statements about the dataset. 5. Estimators for PHR. An estimator is derived for the PHR, replacing the CGM with a model and using Monte Carlo estimates to approximate integrals and quantiles. The algorithm samples new query response pairs and checks if the response is likely under the implied task. 6. Empirical evaluation. The method is empirically evaluated using synthetic regression tasks and natural language tasks with pre-trained LLMs. The PHR estimator is tested for accuracy in predicting the THR and model hallucination rate, as well as the empirical error rate of generated responses. 7. Discussion. The paper discusses the results of the evaluation, highlighting the importance of strong assumptions and potential challenges in using the PHR estimator as a decision support tool. Overall, the method involves defining hallucinations, calculating the PHR, deriving estimators, and evaluating the performance of the estimator in various tasks to assess its accuracy and applicability.
What are the theoretical or practical benefits of using the proposed method compared to existing alternatives?
The theoretical benefit of using the proposed method of estimating the hallucination rate for in-context learning with conditional generative models lies in its Bayesian perspective, which allows for a deeper understanding of the errors a particular application might make. By assuming a joint distribution over all sequences of query and response pairs, the method connects in-context learning to Bayesian statistics, enabling implicit Bayesian inference. This perspective helps in estimating the posterior hallucination rate, which conditions on observed data and provides insights into the probability of generating hallucinations. Practically, the proposed method does not require external information from auxiliary classifiers, making it more versatile and applicable beyond language tasks. It offers a way to estimate the probability of generating hallucinations without direct access to the true mechanism, which is crucial for improving the prediction accuracy of large language models in various tasks such as math, translation, and time series prediction. Additionally, the method provides a finite sample estimator for conditional generative models that only requires evaluating the log probabilities of responses, making it computationally efficient and scalable for real-world applications. Overall, the proposed method offers a comprehensive framework for estimating and mitigating hallucinations in in-context learning scenarios, providing valuable insights for model evaluation and decision-making.
How is the method validated or tested in the paper?
The method in the paper is validated through empirical evaluation. The authors first demonstrate the accuracy of the posterior hallucination rate (PHR) estimator by comparing it to the true hallucination rate (THR) in synthetic regression experiments where the true mechanism is known. They show that the PHR estimator accurately predicts the THR for in-distribution ICL regression tasks and remains robust to different dataset sizes. Additionally, the method is evaluated on natural language tasks using pre-trained large language models, LLMs. Since the true mechanism is unknown in this setting, the authors propose a new metric called Model Hallucination Probability, MHP, to evaluate the PHR against. The PHR estimator is shown to be a good predictor of the MHP for incapability tasks, indicating its effectiveness in predicting the model hallucination rate. The authors also assess the PHR estimator against the empirical error rate and demonstrate its accuracy in predicting the error rate for incapability tasks when certain parameter values are set appropriately. The results of these evaluations provide evidence of the method's validity and effectiveness in estimating hallucination rates in both synthetic and natural language tasks.
What results were achieved with the new method according to the paper?
The results achieved with the new method presented in the paper include the accurate prediction of the true hallucination rate, THR, in synthetic regression tasks, demonstrating the reliability of the posterior hallucination rate, PHR, estimator. The PHR estimator accurately predicted the model hallucination rate in natural language tasks using pre-trained large language models, LLMs. It was also able to predict the empirical error rate of generated responses in incapability tasks, where the LLM performed better than random. The PHR estimator remained robust across different dataset sizes and settings of the parameter value. Additionally, the paper highlighted the importance of strong assumptions underlying the PHR estimator, such as the Definiti representation of the data and the faithfulness of the CGM in estimating the true distribution. The results emphasize the potential of the PHR estimator as a valuable tool for predicting hallucination rates in in-context learning tasks, while also pointing out challenges and areas for future improvement in its application.
What are the limitations or drawbacks of the proposed method according to the paper?
The limitations or drawbacks of the proposed method, as outlined in the paper, include the reliance on strong assumptions. The first assumption is that the in-context learning problem data must admit a Definiti representation. The second assumption is that the conditional generative model, CGM, used is a faithful estimate of the true distribution. Minor divergences between the CGM and the true distribution can lead to underestimation of the posterior hallucination rate, PHR. The paper also mentions instances where properties of the predictive distribution of a pre-trained large language model, LLM, significantly differ from those of the true Bayesian posterior predictive distribution for synthetic in-context learning tasks. These discrepancies highlight a challenge in using the PHR as a decision support tool and suggest the need for future work to improve the robustness of the PHR estimator or optimize conditional generative models for in-context learning.